We're going to be working on related rates, and we're going to start with these two um, problems here involving related rates and how to use implicit differentiation to differentiate the following formula. So let's start with problem number one. We have the formula for area of the circle. So we have A equals pi r squared, and we're going to find dA all over dt, and we are given the value of r, which is 2, and also dr over dt, which is 3. So in implicit differentiation, we are always differentiating with respect to time. So all we have to do is to take the derivative of a with respect to time equal to pi times the derivative of r squared with respect to time. So the derivative of a is dA over dt, and since pi is just a constant, so we just kept it here on the sides. Take the derivative of r squared with respect to time will be 2r times dr over dt. So this is now our derivative function, and we're going to use this in working with our derivatives. So by substitution, we have the value of r, and we have the value of dr dt. So we're going to be able to find dA dt by substitution. So we have pi multiplied by 2 multiplied by the value of r, which is 2, and multiplied by the value of dr dt, which is 3. Therefore, dA all over dt is simply 2 times 2 is 4 times 3 is 12 pi. So this is the derivative of the first problem, 12 pi. Now, to take the derivative of the second problem, let's write out the formula. Here we have A equals 2 pi r h, and we are given r, which is 2, also h, which is 4, and dA over dt, which is 16 pi, and dH over dt, which is 2. And in this problem, we're looking for dr over dt. So that's what we're going to be looking for. So let's take the derivative of a with respect to time. 2 pi is a constant, so let's set it aside, and take the derivative of the product of r and h. So that means we're going to be using the product rule. And to take the derivative of each term, derivative of a is simply dA all over dt. 2 pi is just a constant, so let's set it aside. And now we can focus on the derivative of rh. So we have d dt of r multiplied by h plus r times the derivative of h. So we have dA all over dt of 2 pi times dr all over dt times h plus r times dh all over dt. So this is now our derivative with respect to time for our formula. We can simplify this by distributing this to our equation. So we'll end up with dA all over dt, which is going to give us 2 pi times h times dr dt plus 2 pi times r times dH over dt. And now we're just going to substitute the information that's given to us in our problem. So we have dA over dt, which is 16 pi. H is 4 times dr dt, which is missing, so let's just write dr over dt right here, plus 2 pi, r is 2, dh over dt, which is also 2. Now we can just simplify our equation. 16 pi is equal to 2 times 4 is 8 pi, dr dt, plus 2 times 2 times 2 is 8 pi. And to have dr dt by itself, we'll just use algebra here, so we'll subtract minus 8 pi here. So we'll end up with 8 pi equals 8 pi dr dt, and by dividing both sides by 8 pi, dr dt is simply equal to 1. So this is how we solve equations using implicit differentiation given the dr dt's, or the derivative of the function with respect to time. So we have an air being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. We need to find the rate of change, or the rate of change of the radius when the radius is 2 feet. So we know that we're going to be working with a spherical balloon, so this type of related rates problem will ask us to use the volume of the sphere. And the volume of the sphere is given by the formula 4 over 3 pi r cubed. So sometimes the formula is given in the word problem, sometimes it's not. So you have to make sure that you know your geometric formula in answering some related rates problem. And in this problem, we are also given 4.5 cubic feet per minute, which is the rate of change of the air being pumped inside the balloon. So this will be the derivative of the volume with respect to time, or the rate of change of the volume with respect to time, which is 4.5 cubic feet per minute. And at that instant, we are given the radius of 2, and we need to find the rate of change of the radius at an given the radius of 2 feet. So this is what we're looking for. So let's go ahead and take the derivative of the volume of the sphere. So we have V is equal to 4 over 3 pi r cubed, where 4 pi over 3 is constant. So taking the derivative of V with respect to time equal to 4 over 3 pi times the derivative of r cubed with respect to time will give us dv all over dt of 4 over 3 pi times 3r squared times dr dt. So this is now the derivative function of our formula. All we need to do is to substitute the given information in our problem. We have the dv dt, which is 4.5 cubic feet per minute, equal to let's just copy 4 over 3 pi times 3, and the value of r is also given, which is 2, and we're going to be looking for dr dt. So let's go ahead and simplify our equation. So we'll have 4.5 equal to, we can cancel this out, 2 squared is 4, so this is 8 pi times dr all over dt. So this is now our function. So what we can do, 4 times 4 is 16 pi. So to isolate dr dt, we're going to divide both sides by 1 over 16 pi. So we can cancel this out, so we'll have 4.5 equals dr dt. So that means the rate of change of the radius would be 4.5 16 pi. The unit of measurement will be feet per minute. And if you want to change this into decimal form, we can use the calculator. And 4.5 divided by 16 pi is 0.0895, so we can use it as 0.895. So this is for a spherical balloon. So first we're going to draw the cone. This is the paper cup, and the height of the paper cup is 10 centimeters with the radius at the top at 3 centimeters. So this is very important because this will help us modify the formula for the volume of the cone, because the formula for the cone is going to will be 1 over 3 pi r squared h, and the dv dt, which is the rate of change of the water changing, or when they're pouring it into the cup. So we have dv dt 2 centimeters cube per second, or cubic centimeters per second, and we need to find how fast the water level is rising. So that means the height of the water as it rises from in the cup, so dh over dt, because that's the height of the water, and we need to find it using implicit differentiation. And the height of the water at that instant is 5 centimeters. So these are the information that we have. Now let's go ahead and modify our formula by changing it into a one variable formula for the volume. So the radius is 3 and the height is 10 centimeters. By ratio and proportion, we can have r over h equal to 3 is to 10. And by cross multiplication, we can have the value of r in terms of h, which is 3 all over 10 h. So this is going to be the value of our r that we can use to modify the formula. So our volume now, pi r squared h, is now going to change into 3 over 10h squared times h. So r is now 3 over 10h, and by simplifying the formula, we have 9 all over 100 h squared times h. So we can simplify this, 3 pi 100 h cubed. So now from this formula of the volume of the cone, now we have the new formula for the volume of the cone, wherein we only have one variable to worry about. So now we can take or use the implicit differentiation to solve our related rates problem. So using this, I'm going to take the derivative of v, and since this is a constant, I'll set it aside, times the derivative of h cubed with respect to time. So now we'll have dv times 3 dh over dt. So after getting the derivative, we can use the information now that we have from the word problem. So dv over dt is given, which is 2 centimeters or cubic centimeters per second. So let's change it to 2. And let's just copy the constant. And the height is 5 centimeters squared times dh dt, which is missing. So that's what we're finding in this equation. So now let's simplify this. So 5 times 5 is 25. And we can simplify this and change this into 4. So we'll have 2 equals 9 pi all over 4 times dh over dt. And to isolate dh over dt, we can multiply both sides by the reciprocal of 9 pi over 4. So this cancels out, and we'll end up with 4 times 2, which is 8. 9 pi equals dh over dt. And this is now our dh over dt in terms of pi. And to finalize our answer, because we need the units of measurement here, dh over dt is equal to 8 9 pi. The unit of measurement is centimeter per second. Or if you want to change it in decimal form, 8 divided by 9 pi is 0.2829. So dh 0.229 centimeters per second. So this is how we find the dh dt using implicit differentiation. And for our last problem, this is going to be a different geometric figure once again, and let's go ahead and read the problem. So in this problem, we have a 6-meter ladder that is leaning against the wall. So the first sentence in this particular problem will set up our equation. So this is the wall, and this is our ladder leaning against the wall. And the ladder is 6 meters. So we know that we have a right triangle in this particular figure, and if we have a right triangle, we'll be able to use the Pythagorean Theorem for our equation. So our equation will be 6 squared is equal to legs squared plus legs squared. So the vertical leg, let's label it as y, and the horizontal leg is going to be x. So we'll have y squared plus x squared. So this is the equation that we're going to be using in solving our related rates problem. Now, to continue working on the problem, if its bottom is sliding at a constant rate of 1/2 meter per second, so this one is the rate of change of the distance of the bottom of the ladder. So this will be dx all over dt, which is 1/2 meter per second. How fast is the top of the ladder sliding? So this one is obviously will slide down when if this is sliding away from the wall. So that means we're looking for the change of y with respect to time. And we're going to look at that using implicit differentiation. And the ladder sliding reaches 5 meters up the wall. So at that instant, y is equal to 5, or the height of the ladder is 5 meters. So now that we have set up our illustration, we can now organize our values. We are given the y values, which is 5. We are given the dx dt, which is 1/2 meters per second. Now, using the Pythagorean theorem, we'll be able to find the value of x. So to compute for that, we'll have 6 squared is equal to 5 squared plus x squared. So we'll have 6 squared minus 5 squared is equal to x squared. 36 minus 25 is 11. So x is equal to square root of 11. And that's what we're going to use later in our solution. Now let's go ahead and take the derivative of our equation with respect to time. So take the derivative of 6 squared with respect to time, derivative of y squared with respect to time, and derivative of x squared with respect to time. So derivative of constant is 0. This one is 2y dy dt plus 2x dx dt. And from our information, we have the y, we have the dx dt, and we have the value of x. So let's plug it in. So we have 2 times the value of y, which is 5, dy dt, which is missing, so let's leave it as dy dt, plus 2 times square root of 11 times dx dt, which is 1/2. And by simplifying this, 0 equals 2 times 5 is 10 dy over dt, plus we can cancel this out, square root of 11. So by isolating dy dt minus square root of 11 on both sides, and we'll have negative square root of 11 equals 10 dy dt. And to have dy dt by itself, let's complete our solution. So dy dt is negative square root of 11 all over 10. The unit of measurement is meter per second. And if we're going to change this into decimal, square root of 11 divided by 10 is equal to negative 0.3316. And this is now our